Okay, we are just gonna briefly start this. 5.3, chapter 5 is one of my favorite chapters. It's kind of all about polynomials. So now we're gonna learn more characteristics about polynomials and look at them as polynomial functions, and eventually we'll get to like graph them. So, as a little warm up, we're gonna do this together. I have a division problem here. I have a polynomial of p to the power 3 minus 8 being divided by p minus 2. Look at my divisor. Could I use synthetic division?
Yeah.
Yes, I could. Could I use long division?
Yeah.
Yeah, I can use long division anytime. I'd probably do this synthetically using my outside number of 2. Need quite a few placeholders here. I have a 1 in front of the p to the third. No p squared term, no p term, negative 8. Hopefully I remembered your placeholders on your quiz.
When you use placeholders?
On synthetic division, you have to use placeholders.
I don't.
Was there not one like that?
Yes, there was.
Yes, there was. I was like, I thought there was.
Oh, wait, yeah, there was. I did it.
I think there was.
I don't think there
The
was.
one-
Page.
The one where you had to use synthetic division.
Okay.
I think there, yeah. All right, here we go. 2 times 1 is 2. Add straight down 2. 2 times 2 is 4. Add straight down, you get 4. 2 times 4 is 8. I get a remainder of 0, which means x minus 2 divides perfectly into p cubed minus 8. So my final quotient would be p to what power? Second, good. Plus 2p plus 4, no remainder. This is an honest question. I forget if I taught this in ALG2 or pre-calc. Did we factor cubes? No, we haven't. I remember that. We left it blank on our flow chart. Remember that?
Uh-oh.
Yeah. Okay. No, we're not doing
When's
it.
that
I was
coming
just.
up? You said it was chapter 5.
It might be.
You said it was. You said
It's
what time
not
is it in chapter 5? Don't worry about it.
Not today. Not today. Okay. So basically, we are going to look at polynomials as functions, meaning we're just going to put like y equals or f of x equals in front of these, and now make them something that we can graph. But first, we have to understand some vocab of like what makes something a polynomial. Okay, what makes a function a polynomial? So, in the okay, first of all, you can only have one variable. So if I want to write like a function with just x's, if there was like a term that said like x squared y and it had both x and y, it wouldn't technically be a polynomial. If you had something that was like 5a squared minus ab plus b squared, that wouldn't be a polynomial because there's 2 different variables. So that's like the first thing is it can only be in one variable. Usually it's x if we're talking about functions, right? So we usually write it in terms of x. All exponents, this is an important one. Sorry, question on that?
Are you recording?
Yeah, thank you. All exponents have to be positive integers. Integers are positive and negative whole numbers. Okay, so just positive integers means we can't have negative exponents or fraction exponents. And then all our coefficients are real, meaning we can't have any i's, any imaginary numbers. Okay, so standard form, what this means is the values of the exponents are in descending order. From left to right, like you read a book. I'll show you obviously some examples. Descending order. I do this anyways, and I've kind of been like showing you like, hey, if your largest variable is like a 3, that term should come first, and then it should go in descending order, meaning like your constant should always be last. That's what standard form is. Degree. This is the word I've mistakenly used a lot because I keep forgetting that you guys don't know what this means, but now you do.
Yeah.
Degree is the value of the largest or the greatest exponent. So we just got done talking about quadratics in chapter 4, which is a lot of algebra 2. Oh gosh. Quadratics always had an x squared. Always had an x squared. Sometimes they had another x term, and sometimes they had a constant. Quadratics are degree 2 polynomial functions because their largest power was at 2. Okay, leading coefficient. This is the, do you guys know what a coefficient is, first of all?
Thing in front of that variable.
Yeah, good. The number in front of the variable. Coefficient of the first term when it's in standard form. I often abbreviate leading coefficient as LC. So if you ever see LC, that means leading coefficient. Okay, so here's an example of something that's a polynomial. I'm going to make it a function. So to make it a function, all I got to do is put f of x or y equals in front of the polynomial. So I can only write it in terms of one variable. So if I want to write this function in terms of x, that's what this f of x means. I'm only going to use x's. All of my coefficients have to be real numbers, meaning I can use decimals, negative numbers. I just can't use imaginary numbers. And all of my variables have to have powers that are positive integers. Okay, and I'm going to write this in standard form. So let's say we have a degree 3, meaning my largest power on the x is a 3. And then we go in descending order. So I'm kind of just making up these numbers. But this would be an example of a polynomial function. Okay, let's kind of go through the criteria. I just have x's, right? All of my exponents are positive integers, meaning whole numbers. I have a power of 3, a power of 2. What do I have a power of here? 1. That's still positive, okay? Just can't have any negative exponents or fraction exponents. If you saw something like this, not a polynomial. That's something else. If you saw something like this, also not a polynomial. And I even wrote this in standard form, listing my largest power term first, descending order from left to right. So your constant showing to be last. So what degree would this polynomial function be? 3. Good. This would be a degree 3 polynomial function. What would my LC be, my leading coefficient? 8. Yeah, guys. 8. Not in this case. You can write out degree if you want to, if that's confusing to you. Like that. That'll work. The domain for all polynomial functions is always all real numbers. That's what I like about polynomial functions. Okay, so what do we need? 3 minutes? Some common types of polynomial functions, and you guys have actually seen like the first 3 pretty commonly. So technically we can have a degree 0. Don't let this standard form kind of like notation confuse you. This is just saying if you have f of x equal to some constant number, I'm just going to pick a number. You can pick your favorite number. I did like -7. If I had a function that was y equals -7 or f of x equals -7, whatever, what kind of line would that form on my graph? Show me with your arms. Nice. It'd be a horizontal line. My y value is a constant value of -7, right? So these are called constant functions, where it just equals a constant number. If you want to draw a little sketch, it would just look something like this. A constant rate, constantly -7. Okay, you've graphed those before in Algebra 1. We've graphed horizontal lines too. All right, let's go 1 degree higher. Let's say I have a degree 1, meaning my largest power term is a 1. So I'm just going to do something like this, just making up these numbers. But this would be a degree 1. What would this form on a graph? You're right. I saw you doing it. It would be like a positive sloping line, right? Because my slope here is 5. So these are called linear functions. We know that. You guys do a ton of linear stuff in Algebra 1, and we did a little bit more in Algebra 2. All right. This one we should really know. Degree 2. Nice, Justin. Showing me the U with his hands. Degree 2 would look something like this. Again, I'm just making up these numbers. And that would be a U shape. Either U up or U down, depending on the leading coefficient, if it's positive or negative. Now I can use that vocab, leading coefficient. What types of function are these called? That's the name of the shape. Quadratic.
Yeah.
Okay, we'll leave off there.
Let's go.
Good start.
Yeah, what? Shut up, Nicholas.
Whoa.
Hey, that is not Willis. I don't want to hear that language, Calvin. Thanks, Calvin.